Okay, so now we will complete with part 2 of chapter 8 Sylow Theorems. Last time we were in this corollary. If H is a P group, then H is strictly contained in the normalizer of H in G. We know that H is contained, the inclusion is trivial, so we need only to show that the equality does not hold. Okay, so suppose the contrary, that there is a group H is equal to its normalizer in a bigger group. Okay, H is a subgroup of G, and H is equal to its normalizer in G. Then using the previous lemma, normalizer lemma, we have here NGH index is congruent modulo P to the index of H in G, and so this is equal to 1, which is congruent to the index of H in G modulo P. Now GH is equal to G. Now we can suppose that the order of G is equal to Pn by M. And the order of H is Pi for some I less than or equal to N. Why? Since H is a P group, okay? And a P subgroup, and H must, the order of H must divide the order of G, and so the order of G can be written as Pn by M, where the GCD of P and M is equal to 1. That is equal to Pn minus I M, which is congruent to 0 modulo P. Now, contradicting the fact that this is a contradiction, since we have the index of H in G is congruent to 1 modulo P. And so H is strictly contained in its normalizer in G. Now we start with Sylow theorems. Sylow first theorem. Okay, now for each, let G be a group, finite group. For each P to the power K, dividing the order of G, there exists a subgroup H, subgroup of G, with H, order of H is equal to Pk. This is a very powerful theorem. Okay, now Cauchy's theorem says that if you have a prime number that divides the order of a group, then the existence of a subgroup of order P, that prime, is guaranteed by. But Sylow theorem, first Sylow theorem, is much powerful. We guarantee the existence of a subgroup of order P to the power K for any Pk, where P is a prime number, dividing the order of the main group G. But unfortunately, we lose the fact that the elements or the subgroups we found in Cauchy's theorem are subgroups generated by an elements of order to the power k of order which is power of p. Okay. Now if you have G is equal to 150, then you have a group of order G, subgroup of G of order 5, of order 2, of order 3, and a subgroup of order 3, and also a subgroup G4 of order 5 power 2. Okay. Now we know more about our group G with order 150. Proof. Of course, the identity is a trivial subgroup of G with order equal p power 0, which is 1. So now if we find, we have a subgroup of power with order equal to p power 0 of a G. Now, to prove Sylow's first theorem, we need, starting from a group H1, be a subgroup of a G with order p power I, we will construct a subgroup H2 of order pi plus 1. So we need to construct pi plus 1. Okay. Now we need to show that if you have a group G, then and suppose that the order of G is equal to p power n by m and you need to find a subgroup of order pk where k less than n. So you need to find a subgroup, of course, containing the identity of order pk. Now if you find for any pi, for any subgroup of order p power I, a subgroup of order p power I plus 1, then you cover and then we are done. Actually, then we are done. Okay, so starting from a subgroup H1 with order p power I, as we said, we will construct a subgroup of order p to the power I plus 1. Now start from this trivial subgroup, we can construct. So if we prove the following claim, we can construct a subgroup of order P2, P power 2, then P power 3, then a nested chain of groups. Then we end up with a subgroup with order P power K, as mentioned in the statement of Sylow theorem. So we'll start the proof. Let pi be the following map. So we know that H is normal in NGH, and so this is a well-defined quotient group defined by okay. We have P divides the order of NGH by H. Then there is an element A in NGH such that AH, this group, is of order P. That's Cauchy's theorem, okay? AH is cyclic, of course, equal to H, AH, AP minus 1H. Now, the inverse image or the pre-image of AH is equal to the inverse image of H, etc., the inverse image of AP minus 1H. Each one of size equal P power I. This is of size equal P power I, and here we have P elements. So take H2 to be the inverse or the pre-image of this subgroup. Now these sets are disjoint, of course. These sets are disjoint since the cosets partition H, and so AH, let's say, for example, intersect A power MH or NH or RH is equal to phi. These sets are disjoint all, and so each one of size pi, and then the order of H2 is equal to the number of these sets multiplied by the size of each one, which is equal to P by Pi equal P power I plus 1. Of course, this is a subgroup of the normalizer NGH. Subgroup of G also. Of course, pi is a morphism. And so we are done. Now, having any group or G, let's say you have a group G, then starting from the identity element, you can construct a subgroup of order P, then a subgroup of order P2, a subgroup of order P3, and so on. Nested chain till the maximal group, or till a group with maximal power Pn, group H, with order P power n. This group now is called a Sylow P subgroup of G. Okay, so we have G of order Pn by m, for any k less than or equal to n, P power k divides G, and Sylow first theorem implies the existence of a subgroup of order P power k, and then we can construct a nested chain of P subgroups till the maximal subgroup or maximal subgroup of power having order power of P, which is order of H is equal P power n. Such groups are called a Sylow P subgroup of order P power n. So now the set of all Sylow P subgroups of G is denoted by the set of all Sylow P subgroups of G is denoted by Syl PG. Okay, now theorem, the second of Sylow's second theorem. If H K in Syl P G, then H is isomorphic to K. Proof or equivalent conjugate to K. Okay, conjugate, I mean by isomorphic conjugate to K. Now let H and K be in Syl P G. Consider the set S defined by HG such that G in G, set of right cosets of H in G. Now K acts on S via phi. What's phi? This map from each K, small k in the group K, acts on a right coset in S in this manner. So this is a well-defined map, and this is in S, of course. Okay, so now a fixed point of this action. What is a fixed point of this action? A fixed point of this action is a right coset, of course, is a right coset HG such that HGK small k is equal to HG for all small k in the Sylow P subgroup K. Okay, this is equivalent to say that G K G inverse is a subset of H or equal to H, and the order of H, of course, is equal to the order of K because they are all because they are both in Syl P G. Okay, so they have the same order. Then GK G inverse is equal to H. Okay, so it's enough to show that this action actually has a fixed point. If this action has a fixed point, at least one fixed point, then as you see here, the two groups will be conjugate. Okay, okay. Has a fixed point. Okay, so we know that from P group lemma that the order of the number of the fixed point of points of this action is congruent modulo P to the order of the defined group S, and this is the P group lemma we took in part 1, chapter 8 part 1. Okay, now and S, the order of S is equal to the index of H in G, which is equal to P power n by m, supposing that the order of G throughout. Okay, we can suppose here in this chapter that the order of group G is equal to P by n, P power n, sorry, by m, where P and m are relatively coprime numbers. Okay, coprime numbers, and this is over P power n. Why? Since H is a Sylow subgroup, P Sylow subgroup. Okay, so Pn by Pn, which is equal to m, implies fix phi is congruent modulo P to the order of S, which is m. This is different than 0, of course, or they're not congruent to 0 modulo P, since m and P are relatively prime. And so we have at least an element or a fixed point of the map phi, and we are done. Establishing the result. So now any two Sylow subgroups, Sylow P subgroups, are conjugate. Theorem: Sylow third theorem. Let NP be the number of P subgroups of G, then MP divides the order of G, and MP is congruent to 1 modulo P. So you can say that NP divides M. Okay. Again, order of G is equal to P power n by M. MP divides the order of G. MP is congruent to 1 modulo P. Then NP divides M. Okay, so we are going to say that if MP is a number of P subgroup of G, then MP divides M. Okay, this is an alternative. Okay, so now proof. The group G acts on Syl PG via phi GH conjugation. Okay, so we consider the action phi of G on Syl PG defined as you see here, and we will apply Sylow second theorem, and we will complete the second time.